From space, it looks almost trivial. The narrow Strait of Gibraltar, where Europe and Africa nearly touch. At its tightest point, the distance is just 9 miles, or about 14 kilometers. That is shorter than many bridges that exist inside a single city. Humanity has conquered far greater distances. We've built structures that span over 100 miles of complex terrain. So why, for centuries, has this tiny, obvious connection between two continents remained an empty space on the map? The answer is that the distance you see is a deceptive illusion. The real challenge isn't the width of the strait, it's what lies hidden, its staggering depth, the violent forces moving within the water, and the restless earth on the seafloor below. This short gap is one of the most difficult engineering problems on the planet. On a clear day, from the southern tip of Spain, you can see the mountains of Morocco. The other continent is not a distant abstraction. It's a physical presence on the horizon. This tantalizing closeness has fueled a dream for nearly 2 centuries, a permanent link between Europe and Africa. The ferry that currently connects them takes as little as 35 minutes, a journey shorter than many daily commutes. For generations, the vision has been clear: a bridge or tunnel that would turn this short sea crossing into a seamless flow of trade, tourism, and culture. The idea isn't new. It was first seriously proposed in the late 19th century, and since 1979, Spain and Morocco have had a joint committee dedicated to studying its feasibility. The project has always been framed as more than just concrete and steel. It's a symbol of unity, a monumental piece of infrastructure that could redefine economic relationships and connect 1.4 billion Africans with 450 million Europeans. On a two-dimensional map, the task looks deceptively simple. Engineers draw lines like this all the time. The shortest route, between Punta de Tarifa in Spain and Point Sires in Morocco, is a mere 14 kilometers. It seems like a textbook engineering challenge, waiting for the right budget and political will. For decades, this is exactly how engineers approached it. They treated it as a standard, albeit ambitious, bridge-building problem. They surveyed the 14-kilometer gap, drew their preliminary plans, and prepared their calculations based on the world's most impressive long-span bridges. But when they sent the first probes down to map the seabed, they didn't find the gentle, sandy slope they expected. They found a chasm. And at that moment, the 14-kilometer project became a 900-meter deep nightmare. That 900-meter depth transforms the project from an ambitious bridge into a near-impossible vertical construction. To understand this scale, imagine the world's tallest building, the Burj Khalifa in Dubai. Now, picture trying to build a support pillar even taller than that, but starting from a construction barge tossed around on the open sea, lowering materials into total darkness and through nearly a kilometer of water. The pressure at that depth is over 1,300 pounds per square inch, a crushing force that would obliterate conventional underwater equipment. The fundamental principle of a bridge pier is to transfer the immense weight of the structure down to solid bedrock. On land, this is a routine engineering task. But at the bottom of the Strait of Gibraltar, it becomes a monumental challenge. Engineers would have to build foundations in an environment as remote and hostile as the deep ocean, all while supporting a structure reaching up toward the surface. The longest suspension bridge in the world, the 1915 Çanakkale Bridge in Turkey, has towers founded in water just 45 meters deep. The Strait of Gibraltar is 20 times deeper. Faced with this chasm, engineers studied alternative routes. Some proposals suggested a much longer 23-kilometer path further west, hoping to find a shallower seabed. But shallow is a relative term here. Even on this extended route, the depth still plunges to over 300 meters. This is still 5 to 6 times deeper than the foundations of any major suspension bridge ever built. The static problem of depth alone places the project at the very edge of, or far beyond, modern engineering capability. But engineers are problem solvers. Some have theorized that with futuristic technology and unlimited budgets, the depth challenge could, one day, be met. However, the water in the Strait of Gibraltar is not still. It is home to one of the most powerful and complex current systems on the planet, an invisible, two-layered force that would try to rip any structure apart. This system is a unique hydrological phenomenon. The Atlantic Ocean and the Mediterranean Sea are two massive bodies of water with different properties. On the surface, a powerful current of less dense Atlantic water flows eastward into the Mediterranean to replace water lost to evaporation. But deep below, a countercurrent of colder, saltier, and therefore much denser Mediterranean water flows westward, spilling out over a seabed ridge and into the deep Atlantic. What this creates is not one current, but two colossal, invisible rivers, each hundreds of meters deep, flowing in opposite directions, stacked one on top of the other. Any bridge pier built to the seabed would be subjected to an unimaginable shearing force. The top portion of the support would be pushed relentlessly toward the Mediterranean, while the bottom portion would be pulled with equal force toward the Atlantic. The structure would be in a constant state of being twisted apart by the water itself. And this war is fought on two fronts. While the deep-sea river tries to tear the foundations apart from below, a horizontal hammer attacks from above. The geography of the strait, with high terrain on both the Spanish and Moroccan sides, creates a natural wind tunnel. This funnels and accelerates the famous regional winds, the Levante from the east and the Poniente from the west. These are not gentle breezes. They are sustained, powerful gales that can reach near hurricane speeds for days on end, battering anything that stands in their way. A bridge deck, miles long and suspended high above the water, would be under constant, violent assault from the air. A structure fighting a perpetual battle against water and wind is already at the edge of engineering possibility. But the most terrifying threat in the Strait of Gibraltar isn't the one that flows or blows. It's the one that comes from the very foundation of the Earth itself. This location isn't just a meeting point for water and wind. It's where entire continents collide. The Strait of Gibraltar sits directly on top of the Azores-Gibraltar Transform Fault, the active tectonic boundary where the African plate is relentlessly pushing northward, grinding against the Eurasian plate. This is not a dormant geological feature. It is a live, dynamic fault line. Geologists warn that this zone is capable of producing catastrophic seismic events. The most terrifying precedent is the Great Lisbon Earthquake of 1755. An event so powerful it generated a tsunami that devastated coastlines across the Atlantic. Any structure built here, a multi-billion-dollar project meant to last for centuries, must be designed to withstand a major earthquake. This requirement alone elevates the engineering challenge to an almost unprecedented level for a long-span bridge over deep, unstable water. But even if engineers could design a structure that could survive the earth shaking, the warring currents, and the violent winds, they would still have to contend with a constant man-made danger on the surface. The Strait of Gibraltar is not an empty expanse of sea. It is one of the busiest maritime choke points on Earth. It is a superhighway for global trade, with over 100,000 vessels passing through it every year. That's nearly 300 ships every single day, including some of the largest oil tankers and container ships ever built. Imagine the logistical nightmare of construction. For over a decade, work would have to take place in the middle of this 24/7 flow of massive ships, where a single miscalculation could lead to an environmental and economic disaster. And once completed, the bridge piers themselves would become permanent, immovable hazards in this narrow channel. The risk of a catastrophic collision would never be zero. So let's summarize the physical problem. You must design a structure with foundations nearly a kilometer deep. It must withstand two massive, opposing deep-sea currents trying to tear it apart. It must endure hurricane-force winds channeled between two continents. It must be built to survive a 1 in 500-year earthquake on a major fault line. And you must construct and maintain it in the middle of a perpetual parade of supertankers, with a hostile seabed, warring currents, violent winds, an active fault line, and a constant stream of massive ships. The physical case against a bridge seems overwhelming, and yet the studies have never completely stopped, because the final and perhaps most complex part of this puzzle isn't rock or water, it's us. This is the sober reality that the joint Spanish and Moroccan government committees have faced for over 40 years. Their continuous studies have repeatedly led to the same conclusion. A bridge, given the combination of these extreme forces, is not currently feasible. The challenge isn't just technical, it's economic on a scale that is difficult to comprehend. Projections for a bridge don't run in the millions, or even single-digit billions. They start in the tens of billions of dollars, with some estimates exceeding 30 billion, not including the astronomical, unending cost of maintenance for a structure under constant assault from the elements. This is before even factoring in the political complexities of managing a permanent, binational megaproject of this magnitude. Confronted with this, engineers turned their attention from the sky to the seabed. To bypass the wind, the waves, and the shipping lanes, the most logical alternative has always been a tunnel. For decades, this has been the most seriously studied option. A subsea railway tunnel would be immune to the gales and would eliminate the risk of ship collisions. But drilling under the Strait of Gibraltar simply trades one set of colossal problems for another. Extensive geological surveys of the seabed have revealed a frighteningly unstable environment for tunneling. Instead of solid, predictable rock, engineers found complex and treacherous subseabed geology, including vast deposits of soft, unstable clays. These materials behave more like a pressurized fluid than solid ground, making it incredibly difficult and dangerous to bore a tunnel through them. The active tectonic fault line, the same one that threatens a bridge, presents an even more direct risk to a tunnel buried within the earth. The feasibility of a tunnel, while avoiding the surface chaos, remains heavily debated for these profound geological risks. The Strait of Gibraltar is the ultimate case study in misleading distance. It's not that engineers cannot defeat 14 kilometers of water. It is that in this one specific location, nature has concentrated a perfect storm of deep water, powerful currents, seismic risk, and hostile geology. When combined with the logistical, political, and staggering economic costs, the project shifts from difficult to profoundly impractical with current technology. The unbuilt crossing is not a monument to failure, but a powerful lesson. On a planet like ours, the shortest distance between 2 points is sometimes a nearly impossible path.